to another lecture of the course Mathematical Aspects of Biomedical Electronic System Design. We are now going through the module on probability and random variables. In today's lecture, we will cover random variables, cumulative distribution functions, discrete and continuous random variables, probability mass functions, probability density functions, etc. So let us start today's lecture. We will start with the notion of random variables. To understand random variables, let us recall the notion of probability space. Recall that probability space is a tuple omega, script f and p, where omega is sample space, f is event space, and p is a probability measure. Let us consider functions from sample space to real numbers. So on one side we have space of sample points, on other side we have the space of real numbers, and x is a mapping from omega to r. Let us fix a point small x on r and look at all the points, all the sample points in omega that are mapped to the segment minus infinity to x. So basically we want to see all the points here that are mapped to this. The collection of these points is called pre-image of minus infinity x. The collection of points omega in capital Omega such that they are mapped to minus infinity to x segment, that is x omega is less than or equal to small x. This is called pre-image of minus infinity to x. It is denoted by x inverse minus infinity x. Okay. Now this pre-image may or may not be an element of f, that is event space. X inverse minus infinity x may or may not belong to f. Let us understand it with an example. Consider the random experiment of tossing a die. In this case, the sample space is 1, 2, 3, 4, 5, 6. Let us consider the event space f to be empty set omega 1, 2, 3, 4, 5, 6. Now we consider a function x from omega to r defined as follows. We define x omega to be ceil of omega by 2. Note that for a number z, its ceil is the smallest integer that is greater than or equal to z. Ceil of z, it is smallest integer that is greater than or equal to z or equal to z. For instance, ceil of 2.3 is 3, ceil of 2 is 2, ceil of 2.01 is also 3. Okay. We consider a function x omega which is ceil of omega by 2. So clearly such a function would map the sample space to real numbers as follows. 1, 2, 3, 4, 5, 6. This is my sample space. 1 and 2 will be mapped to number 1. 3 and 4 will be mapped to number 2. And 5 and 6 will be mapped to number 3. In this case, if we consider pre-image of minus infinity 1, it is clearly the set 1, 2, and as we can see it is in the event space. On the other hand, if we consider pre-image of the set minus infinity 2, it is 1, 2, 3, 4. Right? Because all these numbers 1, 2, 3, 4 are mapped to either 1 or 2. Now 1, 2, 3, 4 is not in script F. Similarly, if we consider pre-image of minus infinity to 2.5, this will also be 1, 2, 3, 4. This is also not in F. So we see that pre-image of x inverse minus infinity x may or may not belong to the event space. The special functions for which pre-image of minus infinity x is always part of the event space are called random variables. So let's write this definition. X from omega to r such that pre-image of minus infinity to x is part of the event space for all x in R is called a random variable. Let us illustrate this definition of random variables with a few more examples. Let us again consider the experiment of tossing a die. As before, the sample space is 1 to 6. Let us consider the event space to be empty set, the whole set 1, 3, 5 and 2, 4, 6. It can easily verify that such a set script F is a sigma algebra, that is, it is an event space. Now let us define a function x from omega to r as follows. X of omega is 1 if omega is divisible by 3 and 0 otherwise. Clearly, under this function, 1, 2, 4 and 5 are mapped to number 0. Whereas 3 and 6 are mapped to number 1. Now, if we consider pre-image of the set minus infinity x, then it is collection of all points that are mapped to points on the real line that are either 0 or left to 0. So this pre-image is 1, 2, 4, 5 and it's not in F. So x is not a random variable. However, let's consider the following example. Again, as before, omega is 1 to 6, but the event space now is empty set, whole set 1, 2, 4, 5, 3, 6. Now it can be checked that for any small x on real line, pre-image of the set minus infinity x will be part of script F. For instance, x inverse minus infinity minus 1. This would be set of all points whose image is less than or equal to minus 1. So this is clearly empty set. No point has image less than or equal to minus 1. X inverse minus infinity 0. Pre-image of minus infinity 0. This would be 1, 2, 4, 5. And this is now clearly an element of the event space. Similarly, x inverse minus infinity 1, this will be the whole space omega. So clearly this is also in script f. In the same way, we can check that pre-image of any set of the form minus infinity comma x will be an element of the sample space. So x is a random variable. So this x is a random variable. Let's consider yet another example. I keep the sample space same as before, but my event space is the power set of omega. But my event space is the power set of omega. That is, it is collection of all subsets of omega. In this case, if we consider any x that is from omega to r, since x inverse of minus infinity to x, that is pre-image of minus infinity to x, will certainly be a subset of omega. It is certainly an element of the event space. In this case, x is certainly a random variable. So we see that the same function from omega to r may or may not be a random variable depending on the event space. Now consider any subset B of R such that its pre-image is an element of the event space. For example, B could be of the form minus infinity x, or B could be of the form x1, x2. It can be seen that if x is a random variable, then for all such sets, their pre-image will be elements of event space. In this case, probability of the pre-image, that is probability of x inverse B or probability of set omega in capital Omega such that x omega is an element of B, is often simply written as probability of x in B. Okay. So whenever we see a notation probability of x being element of a set B, we should understand that it means the probability of the pre-image of B. Let us see an example. Let us again consider the example of a die being tossed and event space to be the power set of the sample space. As in the first example, we consider a function from omega to r defined as x omega equal to CL of omega by 2 for all omega in capital Omega. Then pre-image of the set 2, 3 will be collection of all sample points that are mapped to numbers between 2 and 3, that is that are mapped to 2 or 3, and it can be easily observed that this pre-image is 3, 4, 5, 6. So by probability of x into 3, also written as probability of x lying between 2 and 3, what we mean is probability of this pre-image 3, 4, 5, 6, and clearly in this example the probability of this set will be 4 by 6. Next, we consider the notion of cumulative distribution functions of random variables. Cumulative distribution function. Let us consider a probability space and a random variable x that is mapping from omega to r. for all x in R, from the definition of random variable, x inverse minus infinity x, that is pre-image of minus infinity x, is an element of script f, and so its probability is defined. Moreover, the probability is the number between 0 and 1. So we can define a function capital F from R to 0 1 as follows. F of small x is nothing but this probability, x inverse minus infinity x closed interval for all x in R. This function is called cumulative distribution function of x. Cumulative distribution function, in short CDF of x. Notice that f of x is nothing but probability of this set omega in capital Omega such that x omega is less than or equal to x, or in short its probability of x less than or equal to small x. Let us see a few examples. The first example is the die tossing example seen before. Here omega is 1 to 6. We take script f to be the sigma algebra, and as in the first example we consider the function x omega to be CL of omega by 2 for all omega, capital Omega. We have already seen that such an x qualifies for a random variable. We can define the cumulative distribution function f of this random variable as follows. So for instance, f of 2 would be probability that x is less than or equal to 2, which is nothing but probability of the set 1, 2, 3, 4, and this will be 2 by 3. F of 2.5 will be probability of x less than or equal to 2.5, which will also be probability of the same set 1, 2, 3, 4. So it will also be 2 by 3. F3 will be probability of x less than or equal to 3. This will be probability of the whole space, so it will be 1. In fact, it can be seen that the function f looks as follows. So here we have points 0, 1, 2, 3. Here we have 1 by 3, 2 by 3, 1, and f is of the form of a step function value of this function at x equal to 1 is 1 by 3. The value of this function at x equal to 2 is 2 by 3, and the value of the function at x equal to 3 is 1. The value of the function at all the points below 1 is 0, and value of the function at all the points above 3 is 1. So this is the cumulative distribution function f of the random variable that we define. Let's see another example. Now we consider the experiment of a point being selected uniformly from interval 0 to. A point is uniformly selected from 0 to. We consider random variable x, that is a mapping from 0 to R, defined as follows. X of omega is omega for all omega in 0 to. In other words, this f takes elements from an interval 0 to and it maps them to elements in R, and any point omega in 0 to is mapped to omega in R. In this case, we can define the cumulative distribution function f of the random variable x as follows. F of 1 will be probability that x is less than or equal to 1, which is same as probability of the set 0, 1. And since the point is uniformly selected from 0 to, this probability would be half. Similarly, f of 1.5 will be probability of the interval 0 to 1.5, and this will be 1.5 divided by 2. F of minus 1 will be probability of x being less than or equal to minus 1, and that is probability of omega such that x of omega is less than or equal to minus 1. Clearly, for no value of omega, x of omega is less than or equal to minus 1, so this probability will be 0. F of 3 will be probability that x less than or equal to 3, that is probability of the whole space omega, so it will be 1. In fact, it can be seen that the cumulative distribution function f in this case looks as follows. It is a ramp function between 0 and 2. Starts at 0, it ends up at 1. It's a flat line outside this interval. Let's see yet another example. Now we consider the experiment of a coin being tossed twice. It's tossed twice. Clearly, in this case, the sample space is HH, HT, TH, TT. We define a random variable x that is a mapping from omega to R as follows. X of omega is number of heads in omega. In other words, we have a set HH, HT, TH, TT, and x is a mapping from this set to set of real numbers, where HH is mapped to 2, HT and TH are mapped to 1, and TT is mapped to 0. In this case, it can be seen that CDF of x, fx, will have the form as shown in this graph. So we'll have points 0, 1, 2, and fx will be the form of a step function with step size as being half. So this is half, half. F of 0 is 0, f of 1 is half, f of 2 is 1. Similarly, we can define another random variable y to be number of tails in omega. So y of omega is number of tails in omega. So now the function y looks as follows. Its domain is same as that of x, but it maps HH to 0, HT and TH to 1, and T2 to 2. Clearly, x omega is not same as y omega for all omega. This means x is not same as y. The random variables x and y are different. However, if we consider the CDF, cumulative distribution function of y, say fy, then fy turns out to be same as fx. In other words, fy of x is equal to fx of x for all x in R. So we see that if two random variables have same CDF, that doesn't mean that they are identical. So two random variables can have same CDF without being identical. Let us now see a few properties of cumulative distribution functions. Properties. First property, which one can see immediately, is fx is greater than or equal to 0 for all x in R. That is, CDFs are non-negative. The second property is, if x1, x2 are real numbers such that x1 is less than or equal to x2, then fx1 is less than or equal to fx2. That is, CDFs are monotonically increasing. The third property is, if, as in the second property, x1, x2 are real numbers and x1 is less than or equal to x2, then probability that the random variable x will be between x1 and x2, that is, probability that x will be greater than x1 but will be less than or equal to x2, will be fx2 minus fx1. Fourth property says that limit epsilon tends to 0, fx plus epsilon is fx for all x in R. That is, CDFs are right continuous. Property number 5 says that if x is in R, then probability that x will be small x will be fx minus fx minus, it will be greater than 0 if f has a jump or a discontinuity at x. Jump at x. Property number 6 says that if probability of x being a real number, that is between minus infinity to infinity, in other words, probability of x being between minus infinity and plus infinity is 1, then limit x tends to minus infinity, fx is 0, and limit x tends to plus infinity, fx is 1. Note that probability of x lying between minus infinity and plus infinity could be less than 1. That is, in general, probability of x lying between minus infinity and infinity is less than or equal to 1. If probability of x lying between minus infinity and plus infinity is less than 1, then x is called improper random variable. Improper random variable. However, we will restrict ourselves to proper random variables. So for us, probability of x being finite will be 1. Let's now see one more property which says that the collection of all the discontinuity point of x, that is, set of all points such that f is discontinuous at those points. Finite or countable. That is, there can be at most countably many jump points of f. For example, let us recall the random experiment of a die being tossed. Here sample space was 1 to 6. Let us assume the event space to be the power set of omega and consider the random variable x defined as CL of omega by 2. Recall that in this case the CDF f of x had the following form: 0, 1, 2, 3, 1 by 3, 2 by 3, 1. So this was fx. Here there are 3 jump points. 1, 2 and 3. The above property says that in general there can be either finite or countably many jump points. Further, let x1, x2 be the jump points or discontinuity points. Points of f, then probability of x being small xi, in short probability of xi, or sometimes also written as pi, turns out to be equal to fxi minus fxi minus. For instance, in the above example, f of 2 is 2 by 3, f of 2 minus, that is value of the CDF just before 2, is 1 by 3. Hence, probability of x being equal to 2 is 2 by 3 minus 1 by 3, which is 1 by 3. Similarly, f of 2.5 is also 2 by 3 and f of 2.5 minus is also 2 by 3. So probability that x will be equal to 2.5 is 2 by 3 minus 2 by 3 and it is 0. So we see that the probabilities of x taking certain values will be non-zero only if those values are jump points. In the following, we will be interested in 2 special types of cumulative distribution functions. The first special type is when f is made up of jumps, say at x1, x2 and flat portions. An example is the above die tossing example. Where f was of the form as desired here. So f here is made up of jumps at points 1, 2 and 3 and it's flat everywhere else. So f is made up of jumps and flat portions. In such a case, the random variable x is called discrete random variable. In other words, x is called a discrete random variable if its CDF is made up of jumps and flat portions. In this case, x is called a discrete random variable. In this case, probability of x equal to small xi or pxi, or in short just pi, turns out to be fxi minus fxi minus 1, and fx can be expressed in terms of these probabilities as follows. fx is summation over I such that xi less than or equal to x of pi for all x in R. The function p that maps these discontinuity points xi's to numbers pi is called the probability mass function of x. Mass function of, for instance, in the above die tossing example, P will be a map from 1 to 3 to R, and P1 equals to P2 equals to P3 is 1 by 3. If x is a discrete random variable, and its CDF, say f, has discontinuities at xi, I greater than or equal to 1, we often say that x takes values xi, I greater than or equal to 1. Then x takes values xi, I greater than or equal to 1. If the discrete random variable x is proper, then clearly summation of pxi over I greater than or equal to 1 is 1. The second type of CDFs that we will be interested in are those that are continuous. So f is continuous. If f is continuous, that is does not have jump points, does not have jumps, then the random variable x is called a continuous random variable. Continuous random variable. So we are now seeing continuous random variables. In the case of continuous random variables, there exists a function f from R to R plus such that cumulative distribution function at a point x is minus infinity to x integration of fx dx. This is true for all x in R. This function small f is called probability density function of the random variable x. This function is called probability density function. In short, PDF of random variable x. Observe that probability of random variable x taking values between a and b in the case of continuous random variable can be written as a to b fx dx. This holds for all a, b in R such that a is less than or equal to b. If x is proper, if the continuous random variable x is proper, then clearly minus infinity to infinity fx dx is 1. The collection of values at which fx is strictly positive is called the support of the PDF F, or often called support of the random variable x. Further, PDF fx is related to the CDF capital Fx as follows. Fx is equal to derivative of capital Fx wherever CDF is differentiable. Let us see a couple of examples. Let us first consider a random variable x, that is a continuous random variable, with CDF capital F given as fx equal to 0 if x is less than 0, x square if small x is between 0 and 1, and 1 otherwise. If we plot the CDF, it looks like this. This point is 1, so is this. As we can see, this CDF does not have any jump. It is continuous, so x is continuous random variable. In this case, probability density function small f can be obtained as fx equals to f prime x at all the points x at which f is differentiable. So this is equal to 2x for all x between 0 and 1, and fx is 0 outside this window. Probability that the random variable x will be between half and 1 can be obtained as f1 minus f half, which is 1 minus 1 by 2 raised to 2. This is 3 by 4. The same can also be obtained by integrating the probability density function as fx dx half to 1, that is 2x integrated from half to 1. Clearly it also gives the same result, that is 3 by 4. Let's see one more example. Let us now consider a random variable x, again continuous random variable, whose PDF is a constant between 0 and 1. So it's a constant between 0 and 1. So let's say it takes value c between 0 and 1, and it's 0 outside this interval 0, 1. Such a random variable x is called uniformly distributed on 0, 1. Recall that the PDF must satisfy this relation minus infinity to infinity fx dx should be 1. So in this case, c dx 0 to 1 has to be 1, and this tells that c has to be 1. So the PDF now is fx is 1 if x is between 0, 1 and 0 otherwise. In this case, we can obtain the CDF of x from PDF as follows. Fx will be minus infinity to x, so fz dz. So it will simply be x if x is in 0, 1. It will be 0 if small x is less than 0, and 1 if small x is greater than or equal to 1. Now suppose y is another random variable that is given by x square. So consider another random variable y that is x square. Then CDF of y can be obtained from CDF of x as follows. CDF of y, say fy, can be obtained as follows. Fyy, which is probability that y will be less than or equal to small y. Since capital Y is x square, so this is probability that x square is less than or equal to small y, which is same as saying that x is less than or equal to root y, which is fx root y, which in turn is equal to root y from the graph above. If root y is in 0, 1, or equivalently if y is in 0, 1, it can also easily be seen that fyy is 0 if y is less than 0, and it is 1 if y is greater than or equal to 1. From the CDF of y we can obtain its PDF by differentiation. So PDF of y, let's say small fy, can be obtained as follows. Fyy is derivative of capital Fyy, and this turns out to be equal to 1 over 2 root y if y is 0, 1. It's 0 if y is less than 0, and 1 if y is greater than or equal to 1. In general, we can have a random variable that is neither continuous nor discrete. In general, there can be a random variable x, say x, there can be a random variable, say x, that is neither discrete nor continuous. In other words, such a random variable will have discontinuity points say xi, I greater than or equal to 1, and also a function small f, a function small f from r to 0, 1, such that its a CDF fx is equal to summation over all I, such that xi less than or equal to x pxi plus fz dz integrated over minus infinity to x for all x in R. In this case, if x is proper, then summation over I pxi plus integral from minus infinity to infinity fx dx is 1. Let us consider an example. Suppose a point is uniformly picked from interval 0 to 2, and I define a random variable x as follows. Define random variable x as follows. X of small omega is equal to a round of omega if modulus of omega minus round of omega is less than or equal to 0.2 and its omega otherwise. Let me tell what we mean by round of a number. So for all x in R, round of x is defined to be the nearest integer. Nearest integer of x. For instance, round of 1.2 will be 1, 2.9 will be 3, round of 3 will also be 3. So we define a random variable x omega to be round of omega if omega minus round of omega, absolute value of this difference, is less than or equal to 0.2 and x of omega is omega otherwise. It can be checked that x is neither continuous nor discrete. Check that the random variable x is neither discrete nor continuous. We will not continue this discussion as we will only be interested in random variables that are either continuous or discrete. In other words, we will not consider such mixed random variables. This brings us to the end of this lecture. Thank you.